All right, today we're going to talk about biomes, get those under control. We'll start with taking a quick little look at this photograph. It's a very famous photograph from one of the later Apollo missions. I think the caption says Apollo 17 or something. I'll put the caption up. Yep, there it is, Apollo 17. And so when you look at this figure, what you're seeing is basically the east coast of Africa. Let me get over here. There's the east coast of Africa coming down here, the Cape around here. Over here, this is going to be Madagascar, the Arabian Peninsula right up in here. And so you get kind of a sense of what's going on. The southern pole is going to be down here, and so this is Antarctica. One of the things that I want you to be aware of just looking at this kind of incredible photograph is the amount of clouds, the amount of ocean there is. What you realize, of course, is that most of the world is going to be ocean, right? And maybe 25% of the world is covered by land, but the rest of it's submerged. Now, when you think about all this water, then when the sun is shining on it, we got evaporation, and so we're going to get an awful lot of clouds that are going to be created over all this wet part of the world, right? And then, of course, the winds are going to blow over the continents, bringing a lot of the oceanic-derived clouds over the land, which is a good thing, all right? All right, so we'll put that one aside for the moment. And here are the next pages of notes. And so you'll find a new set of notes under materials for exam 2, part 2, and this should be the first page of it. And so we come back to a phrase, the most explanatory abiotic factors for distribution and abundance, right? So when we have a study of distribution and abundance of organisms, we probably are going to be thinking, oh, that's kind of a definition that you could use for ecology. And so when we're looking to see how organisms are distributed, sunlight with its attendant temperatures and water are going to be the two biggest factors that are going to determine whether an organism can live in a particular area or not, right? So these are going to be kind of limiting factors that are going to determine what organisms live where. Now, these factors, water and the temperature, the sun, water, and temperature, these are basically what we think of when we think of what factors form the climate, all right? Now, climate and weather, two different things. Weather is going to be, our daily, it's raining today versus, oh, it's sunny today. Climate is going to be, well, what's your summer like? It's going to be, hot and humid and, fairly moist with rain. The summer is going to be a lot rainier, far more precipitation. Winter's going to be moderately cold, right? And so you talk in general terms. If you describe the climate, you could be describing like what that month is going to be like within the season, right? And so when people talk about, oh, a Mediterranean climate, you know what they mean. They think, yeah, here we are in Greece, here we are in Italy, Mediterranean countries where it doesn't really get cold, bitterly cold in the boot of Italy, or, really, really hot. You got all the moderating winds that are going to keep it cool in the summer and warm in the winter. The same thing with, here's San Diego, or, maybe some of the eastern seaboard states, that are kind of southern, well, a little bit more temperature. But if you go in the mountains, well, it might seem more Mediterranean-like, right? But people know, if you talk about continental climate, continental kind of gives you that feeling of Kansas and Nebraska and the Dakotas, where, it's real cold in the winter, down to minus 20 degrees Fahrenheit easily during some of the worst of January. And during the summer, you can get days that are 100 degrees. And generally, you don't think of it as too terribly humid, but, well, it depends on where you are in the mid-continent. But, continental climates, maritime climates. Yeah, New England, maritime climate. You get the sense of it. Climate, and overall, what's the year like? What's the season like? Weather, it's day to day. What is the weather today? Okay. When we look to see what the climate is like, what the long-term temperature and rainfall is going to be, precipitation, we think solar radiation. And so I showed you this once before. Basically, you imagine, 1 astronomical unit away, we have the sun very far away from the Earth. But the sun is so huge, hundreds of Earths could fit inside the sun. The sun is that big. And so when it is beaming out its nuclear fired sunlight, then basically it's a stream of beams of light that is coming in, all perpendicular to the Earth. And so when we look at the Earth now, we see, yep, along the part that, we've got this horizontal part of the Earth that is perpendicular to the sun rays. And then we have up here, something that's a little more at an angle to the sun rays. Well, right here, you're going to get more sunlight per square meter than you have over there, right? It's spread further out. We talked about the solar constant earlier in the semester. And so again, you think, well, there's a square meter here and it's being spread over, this long amount of surface area, whereas this shorter amount of surface area, that same 1 square meter at the outer atmosphere, right, the solar constant, that is being spread over a much smaller actual area. Now, what does that end up doing for us? When we look here, we can think there's the equator, and the sunlight is coming in, and it's really warming things up intensely on the equator, either to the north or to the south. Yeah, we're getting a little bit of the curvature of the Earth, and it's slightly cooler down there. So most of the warmth is right here. And what's going to happen? Particularly if you're over the ocean, you're going to get an awful lot of evaporation. If you're over the land, well, you got the trees, the grass, the vegetation, and you may have evapotranspiration, right? So transpiration by the plants along with evaporation coming off the plants or the land or the inland lakes and streams or whatever. But a lot more water coming up off the oceans. And so that warm air down here rises, right? It's warmed up, it becomes less dense air is going to rise upward. And with it, it's going to carry all that water moisture, all that vapor. Now, as it gets higher and higher up in the atmosphere, well, it starts to lose heat. You're getting closer to outer space and it's cold out there. And so you're losing heat as you go further and further up, and the water molecules are going to condense. They're going to end up slowing down here. The heat, the warmth at the surface of the equator cause those water molecules to just kind of vibrate real fast. And so, all the air molecules are vibrating fast, and that makes them, less dense, and up they go. Now, when you cool things off, well, molecules don't move that fast. And so that gives time for the water molecules to attach. They cling to each other. They don't break apart quite as easily in this relatively colder, less volatile atmosphere. And so clouds form. You've got, condensation. Now, you got cold air here, but there's all this warm air that keeps coming up. And so what happens is that the cool air gets shoved over to the sides, and the cool air eventually is going to start falling back down. And we end up on the ground. We move over, the winds are blowing, and we warm up again, and we rise. And then we just keep going around and around. And so around the equator, this is referred to as a Hadley cell, right? Oh, this is a nice figure here too. And so, low pressure because it's less dense air. And so less dense rises and then off to the side and down we go. High pressure area. But look, the water, the air that's coming down, cool air. But something that's kind of interesting is that this cool air is fairly dry, because what happened when you condensed the air over here, you formed all the clouds, and a lot of those clouds, well, they started having rainfall, particularly if you're sending it over the land. You had been over the ocean's fairly flat. Now you go over the land and you're rising up, and this is going to instigate rainfall. All right, we'll talk about that in a little bit too. All right, so that was all a very simplified model, right? When we have an Earth that is smooth, no landmasses, equator oriented, same place in orbit, so equator perpendicular to the sun rays, getting the maximum amount of sunlight per square meter. Well, here we go. This is what I had explained, the air rising, cooling, coming back down. And then when we look at what happens in terms of all the cells that are going to be formed, all the convection currents that you have forming, there's the equator, here's that Hadley cell that had formed with I was going the wrong way, the hot air rising and then descending at around 30 degrees, right? 30 degrees in latitude. So 0 degrees, 30 degrees. And so this is descending. And then take a look here and we see another cell, this one called Faro cell. And so what's going on here is, this air is descending. And then, it's rising here. And so where's it rising over here? Around 60 degrees. And so this is relatively warmer than the polar region. So this polar cell, we've got circulation going on there. So you got 3 big cells of convection currents in the northern hemisphere, 3 big cells in the southern hemisphere. And you realize, of course, that the Earth is rotating around. And so now we add the rotation of the world to that. And we see that these cells, they're going to end up having this little torsional twisting motion going on. Now, again, we put in, here's that water rising, condenses, forms raindrops, falls back down. And so when you look along the equator, you might expect tropical rainforest. Tropical rainforest, are getting just vast amounts of water per year. Now, the dry air coming over and then descending, cooler, dry, well, this is where you find deserts, right? So, tropical rainforest down here in Congo and in Gambia and other, Tanzania and Kenya and all that. Well, now we're getting up a little further, but, rainforest through here. And then as you go further up, well, you get into the savannas and then you get into the desert regions. And so, yeah, here's the Nile river coming through with the delta, and you got Egypt surrounded by desert over here. You got the Arabian Peninsula, and so Iran, Iraq, and Saudi Arabia, and all those other countries again with lots of desert. Now, you look at the winds that are going to be set up by those cells and the twirling of the earth, right? So the earth is going around, the earth is going this way, right? So going that way. And so the winds are going backward here. And so this torsion is going on. And so when the sailors were out there, they were fully aware of what was going on in those big ships during the age of exploration and all. And so they knew, at some areas of the globe, oh, horse latitudes. If you were carrying a bunch of horses in your cargo of your ship, and you were sailing along, and yeah, we get to go pretty nice and fast if we're going in this northeast direction here, or if we're going in this southwest direction here, right? Northeast trade winds, taking the winds coming from the northeast, coming down here, the southeast trade winds, the winds coming from the south and the east, taking us to the north and the west, right? So we got the names going for us here. But up in this region here, this would be kind of between cells where air was coming down, kind of a stagnant area at times. And so the horse latitudes, our horses are starving because we're not getting anywhere. Our sailing ship just isn't moving. And so the horses aren't doing well. We're drinking our water and there's not enough left over to keep the horses going. They're dying of thirst. They're dying of malcontent. They're not happy horses. And so you throw them overboard, right? And so horse latitudes where, sailing ships might have been stranded for a while and waiting for the winds. And if it took a few weeks, well, it was just kind of a bad luck, and everybody was doing poorly on a sailing ship at that point. So we got the names of the various winds that you might have been, aware of. And we'll put that one down, set that one down. All right, taking a look at the notes, okay. Cool, dry air at 30 degrees, warm air at 60 degrees, and then cool, dry air dropping down at 90 degrees. And so we think about what's going on, and here we have a map showing the precipitation. And look at that, around the equator, we have the highest amount of precipitation in bright green, right? That's going to end up being the tropical rainforest, right? Still kind of high precipitation there. 30 degrees down, 30 degrees up, we got deserts. Deserts over here, deserts here, deserts there. So continents with deserts. Now we look through and, mid-continent, yeah, it's really dry in there, the plain states. But look at what's going on up in here. High levels of precipitation along that west coast. And so along that west coast, we have lots of rain. This is where condensation, the warm air is going up, the rains are coming down. We think about, here's England, there's Ireland. And again, this belt of higher precipitation may not be as much as in the desert, but still pretty high. And so there we got a lot of rain. If you're in England, yeah, take an umbrella with you, right? Because it's always going to be raining there. And we got other things that are mitigating what's going on. Before I forget, I wanted to point out, the whole point of putting up the picture was to point out way at the top of the world here. We're at the polar region. And again, it's very dry air up there, very dry. And so you might think, you got all that ice up here. But really what's going on is we've got all this dry air coming down, right? So here's about 60 degrees north. Now we're at 90 degrees north. All that dry air coming down, no moisture. And sure, there's snow here, but if you maybe get an inch of snow a year and it stays frozen all year around, it will accumulate. And so, yeah, we may still have a desert condition, but we are walking on frozen water when we're up in the Arctic, all right, or the Antarctic, because the water is bound. It's kind of in its own little sequestered reservoir. Okay, now when we looked at the map here, it's not perfect. It's not the idealized world that we would have, expected from that model. And so, what is going to mitigate against having that idealized world? And so, here we have some complicating factors, and right off the bat, we know seasons are going to be happening because we got the tilting of the Earth, right? We already saw the spinning of the Earth giving us a lot more interesting wind currents than we had, right? The westerlies and the northeasterlies and all of that. But the tilt of the Earth, well, at one point of the year, the northern hemisphere is tilted toward the sun in its orbit. And then, as it goes around the sun in its orbit, well, at some point it's going to be tilted away from the sun. And so as it spins around in its daily, journey, and it's winter time, that northern hemisphere is facing away from the sun. Yeah, we get some sun for, a few hours of the day, but it isn't the intense sunlight that we get in the summer. And so the seasons are going to complicate, what's happening with, that idealized version. And then that idealized version, if you had a nice, smooth, entirely watered surface, well, it would be, nice Hadley cells, polar cells, all that wonderful convection currents uninterrupted. But we have a situation like this where we have continents. And so, here we come from the west, the air is coming this way, and the air current is coming up and it's getting pushed to heights. As you walk up the mountain, it gets colder and colder and colder as you go higher. The air gets thinner, right? And so what happens? Well, the colder air drops the rain, precipitation, condensation happens to the vapor. You might not have had a whole lot of clouds here, but vapor starts forming more and more as you go higher and higher. And then, in order for that wind to go over the mountain, well, they'll probably end up having a lot of the water lost. Then when you get on the other side of the mountain, look at what happens. Rain shadow. That air has now lost a huge amount of the moisture that it might have contained. And so on the other side of the mountain, the air is very dry. Okay? And so here they're showing us something about the West Coast. Pacific Ocean, small little mountains. We're going to end up having a precipitation event as the air gets pushed up, and then we come back down, and it's a little bit drier here, but then we're pushed way up again because there's two mountain ranges with a big little valley there. And then here's the huge valley, and notice it's pretty dry on this end. We dumped all the rain in two different events back there. And so if we were to look, at that West Coast where we have all that precipitation there, and then inland it's so dry. Well, what went on? Here's Washington, all right? So average precipitation of Washington State, Pacific Ocean here, and so a range of mountains here, and what happens? The darkest colors are going to be, or closer to the blue, darker green. These are going to be high precipitation, so we're dumping the rain through these mountain ranges. A little bit of a lowland here, a little bit drier, not too incredibly dry, but dry enough. And then up over, the wind goes over the next set of mountains, and again we're dumping huge amounts of rain. Forests are growing, it's really wonderful. And so you can find all kinds of temperate rainforests through here. Temperate. Instead of tropical, it's a temperate climate. It doesn't get as hot as the tropics, but you can get a huge amount of rainfall. You look at it, and yeah, 120 inches per year. You go live in Seattle, you have an umbrella. And then you get into the more continental part. We haven't even gotten to the full range of the Rocky Mountains yet, but things are drier here. Go over the Rocky Mountains, again, you're heading, higher, 14,000 feet peaks, are going to be found in the Rockies. And so, yeah, you're dumping what little rain you might have left. And then here in the mid-continent, things are just terribly dry, very, very dry. Okay. Let's see. Bodies of water, lake effect. When we look, where's my picture of the lake effect? All right, we'll do the best we can. The lake effect. We look and we see, all this dry air that's coming through Canada and whatnot. It's coming from the northwest and it's heading down. And in the middle of winter in particular, you got cold air coming down over the Great Lakes. And that air, as it travels over the lakes, it's going to pick up water, right? Because the lakes, they're moderating, they're losing heat all winter long until they, ice over. But even still, they tend to be warmer than the atmosphere above it. So you're losing water from the warm lake into the atmosphere. That cold air continues to go over Erie, right? Lake Erie. You got the town of Erie, the city of Erie. You got the town of Buffalo, and this whole western New York, northern Pennsylvania bit right here. Lots of snow in the winter. Okay, so you got to have a snowblower because you're dealing with multiple feet of snow. Yeah, their winter is 12 feet of snow, and it's due to the lake effect coming across. Ocean currents, while we're here, they are going to be generated. We have all that heating of the surface waters and waters from the Arctic up here. They flow into the ocean as glaciers melt, and the cold, dense waters, they go deep. The surface waters, they're traveling on top. And so we have these ocean gyres. And we take a look here, and we have the Gulf Stream. That's a surface gyre, a surface current that's coming up, and it's going across the Atlantic and basically keeping England, Scotland, Ireland, keeping that whole area right there warmer than you would expect. Look at how high up in latitude they are. You'd be, at the Hudson Bay area, right? Churchill in the Hudson Bay, basically polar bears running around up here. If you're in the continent, it gets real cold, continental climate. If you're over here, the ocean currents, even though we're at the same latitude, keeps us a whole lot warmer and wetter. All right, so much for that. For the moment, we'll come back maybe later on. All right, but it is true, you take a look and you see where all the distribution of the cells are, the theoretical distribution, and then you compare to what the distribution of the precipitation and the heat would be, and it actually matches up pretty well, okay? And so now that brings us to what we're really interested in, the biomes. And so major ecosystems that have characteristic climate, plants and animals, right? Plants and animals, typical, but they're not a specified species. And so we take a look and we go, the Sonoran Desert over here in the southwest of the United States, in Mexico, Chihuahuan Desert, the Great Basin up through here, all this desert area. You take a look and you see these plants that have adaptations for living in a low moisture environment. Cactus, where the body is photosynthesizing, right? The leaves that would have all the little stoma that would allow evaporation to suck the water right out of the plant, right? That would kill the plant. And so you reduce the ability of the sun to evaporate the water out of you. You have these cactus-like plants. Now, you go down here into Africa, oh, we got a desert here, right? Low precipitation, and you start looking, and you have these plants that look like cactus, but they're not the same species. They're a whole different family, a euphorbia family, the euphorbia. And so a lot of people will have a little cactus in their house, but it will be an exotic African euphorb rather than, a North America, pear cactus or something. And so you start looking around at deserts in different areas. Here's, the Australian desert. Over here, the Atacama Desert, the Kalahari Desert, the Sahara Desert. You look up into the Gobi Desert in Mongolia, and basically a lot of the same animal types, because they have to adapt to the environment. They can't survive if they, had a different adaptation. You're not going to find too many, aquatic fish living in the desert. They're not adapted. And so we expect a lot of convergent morphologies in these faraway deserts, in these faraway plains, the plains of savanna, the pampas, the steppes, whatever you want to call, this grass-like area. They'll all have gazelle-like animals, right? Things that graze. They just don't end up being the same species. So convergent adaptations, convergent morphologies, so that they can live in that similar kind of environment, right? And so we look, and a biome is going to be the particular kind of adaptation complex that you might expect. Here in this map, again, we see color-coded that more or less corresponds with the cell map, convection current maps of the winds and the rains, and here the precipitation pattern. But now what we're looking is the biomes. And so tropical rainforest, deciduous, desert in yellow, savanna, tropical scrub, temperate rainforest, coniferous forest, tundra, and then ice, right? The ice is going to be its own little biome. Yeah, down here in Antarctica, we're expecting penguins, right? But we're not expecting a whole lot of other birds that are going to enjoy, breeding in 20 below, 40 below, 60 below degree weather. Seals would be down here. You look up here, again, ice. And we might expect things like polar bears and, again, the seals and walrus and things of that nature. We can anticipate what kind of animals would be adapted to that biome. Tundra, is going to be in red here. Yeah. Tundra, alpine vegetation, tundra there. And so the Alps. The Alps are over here around in Italy and France and Switzerland. That's where you find the Alps. And then getting a little over into Austria and Germany there. But Alps over in that general area. And, you're going to find kind of an alpine distribution there. Tundra kind of high up. All right. Now, we'll talk about, a couple terms before we get to North America here. Endemic animals, these tend to be specific, like the penguin is endemic to that southern ice pack biome, right? You don't find penguins anywhere else. Polar bears, you're in the northern frozen, ice pack, alpine conditions. You're not going to find polar bears anywhere else in the world naturally. They'll be in a zoo, but not naturally. Particular kinds of possums or armadillos or some, they may be endemic to certain biomes. They're not going to be found too far north. You're not going to find an armadillo in the tundra. But there will be animals that you only find in the desert, for example, only in a particular desert that you happen to be in, and that would be an endemic animal. All right, so we can characterize the biome in different ways, and we'll do that, on the next page. But here we go. I wanted to point out, here's a fellow, Dr. Merriam from, died in 1942. He was a very important person in dealing with ecology and mammalogy and all kinds of, biological things back in the turn of the century, the 1900s. And one of the things that he was world renowned for was kind of starting off this whole biome business. And what he was doing was he was walking out west and he was going up and down the mountains here. And so here, the San Francisco Peak, if you are walking along from the bottom where you might have a desert over here, and then you start walking up the mountain, you see that we go through these different life zones. That's what he was calling them, life zones. Different kinds of organisms were adapted to different types of environments that changed as we went up higher. And that change, well, wetter on this side, drier on that side, right? And so, we might have a little tilt, as we're looking at these life zones. Or maybe it's the heat, the warmth, more light on this side, less light on that side, right? These, and temperatures and precipitation, these can change, where the life zones, where the biomes. This evolved into biomes. And we see, yep, alpine, that's going to be snow-covered. Timberline, basically where you're losing trees. They can't survive much up there. And then he was looking at the whole United States, the Hudson River area, spruce, fir forest, Canadian mixed conifer, what was this one, deciduous? Yeah, I don't know what that says. Deciduous pine forest, probably for transition. And then down here we have, the hardwood woodlands with the deciduous trees and all through here. And then, down here we're getting into chaparral. And so chaparral, actually I have a photo here. This is chaparral, getting kind of dry, deserty, what kind of plants, things that don't evaporate, transpire a whole lot of water from them, so they can make do with a little bit of water per year. Kind of a scrubland. That's the chaparral. And you find a lot of it out there on the West Coast. And, if you suppress fires, this is one of the problems out there. You suppress fires, then, the chaparral, all this dry material starts building up, dying, building up. It doesn't get cleared out by little fires. And so you just keep piling up the tinder and the forest and the chaparrals out there. Lightning hits and bam, you've got a fire, and you got, massive problems if you don't let little fires kind of take out small amounts of chaparral, small amounts of woodlands over, small amounts of time, instead of having a huge fire all at once because you hadn't had a fire in 50 years in the area. Okay, so life zones we're seeing, as we go up a mountain, that alpine tundra on the top of the mountain. Well, look at the latitude of, as we go higher and higher in latitude, and we'd see there's that alpine zone, way up here, tundra here, alpine here, tundra here. Basically, we can follow the same life zones going north as he saw going up the mountain. Well, he also saw it going, across the United States too. Okay. And so this particular figure here, I really like. So temperature and rainfall, they are what's critical for biome distribution. And so on this graph, what they're doing is showing us temperatures go from low to high. So high temperature down here, low temperature up there. And then as we go from low rainfall to high rainfall, we're going along the x-axis. And so now, I'm just going to pull that up just a tiny bit more. So now, if we look at the whole thing, and we think, a little bit of focus, there we go. High temperature, low rainfall, well, that sure looks like what you'd expect. A warm desert, warm grassland, warm savanna, warm tropical rainforest. So as we're going across here, more rainfall. The same temperature, but more rainfall. So this would be, down at the bottom of the mountain or near the equator. We go to a little bit lower temperature, low rainfall, cool desert, cool grassland. Yeah, okay. Kind of a deciduous temperate forest. Yeah, all right, well, we're getting there. Temperate rainforest, well, when we get high precipitation, maybe we'll never get as high precipitation as here, but then, don't get that hot either up in the temperate rainforest. As we go further north, okay, now the temperature gets low enough that when the rain does fall, it doesn't just immediately evaporate off. So the trees, yeah, they basically can grow because trees need a lot of water. Grass needs less water. Trees need more, right? And so we see, trees over here with more water, but less water. Well, more trees. And so here, the water did not evaporate from the heat, right? Because the temperature is low. So we can have coniferous forest, the taiga, right? The taiga. And then up here, this is kind of an odd situation that we'll talk about as an example of a biome, the tundra. And, well, we're getting very few trees. And there's a reason. They cannot root very well. You might be able to have as much water as you want, but it's not going to be available to you. All right. And so, biomes of North America, here we have a list, and, we're starting at the far north, we're heading south, so taiga, montane, temperate rain, mixed conifer, sclerophyllus, hardwood forest. So that's kind of what we're used to. The deciduous, they lose their leaves in the wintertime. All right, so before we leave the page, we got your diversity issues. When you're in the tropics, high temperature, high rains, you can have a huge diversity. Lots of different animals can survive there. Low temperatures, harsh conditions for life, low precipitation, you're going to have a much lower diversity. Yeah, there are going to be a bunch of organisms that can live there, but not near as many as could live where it's nice and warm all year round equitable, and there's enough water that you're not going to have a problem. All right, continuing here, temperate deciduous, chaparral, grassland, deserts, and tropical rainforest. And so, now we've gone from North Pole to South Pole, and we've covered quite a few of the ones that are going to be in the United States. All right, distribution, always think temperature, moisture, right? And the temperature going to be brought to you by the nuclear radiation from the sun, that energy flow, that's really what's giving us the moisture, right? Evaporating the water from the oceans, sending up, creating the ocean currents, creating the wind currents. All that is the redistribution of that absorbed energy around the earth. So always keep in mind the flow of energy from the sun warms up and energizes the molecules on the earth, and the earth molecules, warm, rise, cool, fall. That gives us our air currents, gives us the rising of the water, the vapors evaporating, all of that. I cannot emphasize enough. It's just redistributing that energy by warming up the matter of the earth, okay? So it's part of those cycles. The hydraulic cycle, the water cycle, basically driven by the sun. Okay, and then the last thing to deal with the Miriam, the biome distribution, the latitude, parallels, the altitude. And well, just so that you can see here a different way, I showed you the other where you had two axes, one with the temperature, one with the precipitation. This one, here we have a little bit more complexity. Precipitation on this axis. Down here, humidity, right? How much rain or how much moisture is in the air. And then how does that moisture get in the air? Well, it's going to get there either through transpiration from the plants or evaporation. And so what's the potential to evaporate? Well, if it's really, really hot, it's going to, be real high. But if there's not a whole lot of precipitation, right? And so we look in the precipitation, 62.5, 125 millimeters here, 250 millimeters of rain, and then we go in this direction, this is a ternary diagram. If we go in this direction, we see if we have real high potential evaporation, it's going to be real hot, and we're not getting a whole lot of precipitation. We're getting the desert, in different kinds of desert, real extreme, desert scrub, here a boreal desert. Well, it's kind of cool up there. Dry tundra, desert in the polar region, right? We've got very low evapotranspiration. See, 0.5 to 1. Down here, we got up to 32 potential evapotranspiration ratio. You're going to just evaporate or get the water out of whatever is laying out there in the sun down here. Here, not so much. Down here, high rains, right? Annual precipitation, 4,000, 8,000, 16,000 millimeter. Okay, we're looking at rainforest. And we can get rainforests up here, even though we're in the boreal region, even though we're in cooler climates, right? So tropical, polar, midway, cooler climate, but still temperate rainforest. And so kind of a nice little diagram, a different way of showing things. And that's where we'll stop for today. So keep in mind, flow of energy gives us our winds, our rains, our climate. Okay, goodbye.